Okay, we are now going to talk about matrix multiplication. So not scalar multiplication, not multiplying a matrix by a scalar, by a number, but multiplying two matrices together. Okay. So there's a definition. So suppose someone gives you two different matrices which can be multiplied. For two matrices to be multiplicable with each other, they have to satisfy some properties. It has to be the case that if A is a matrix which is M by N, and B is some matrix uh, which is N by P, it has to be the case that the number of columns in the first matrix is the same as the number of rows in the second matrix. This has to be the case. Only then can the matrices be multiplied in this order, in this specific order. Notice, by the way, it's possible for A times B to be multiplicable, but B times A not to be multiplicable. Right? So suppose A is, for example, a 2 by 3 matrix, B is a 3 by 4 matrix, B times A is not defined. This can't be done because B is a 3 by 4 matrix, A is a 2 by 3 matrix, so therefore the number of columns in B is not the same as the number of rows in A. So this is not possible. Anyway, so if A times B can indeed be multiplied, then let's say the resulting matrix C with components Cjk is defined as summation L goes from 1 to n, Ajl, Blk. Instead of looking at the formula, let's look, which is important, but let's instead look at an example and then we'll see what's going on. So for example, suppose A has 4 rows, 3 columns, B has 3 rows and two columns. Then the result of the product of multiplying this first matrix with the second matrix is going to be given by, so for example, the C2 comma 1 is going to be take the second row and of the first matrix and the first column of the second matrix and multiply these two vectors component wise. So C21 is going to be A21 times B11, so these elements, plus A22 times B21, so these two elements, plus A23 times B31, so these two elements. Okay, so this is how you compute this element. Similarly, let's say you wanted to compute C32, then you would take the third row of this matrix and the second column of this matrix and then multiply them component wise. Okay, so that's what the formula here means. The definition of matrix multiplication. This can be summarized by saying that there's a couple of examples here. So, for example, if A times B, so if I want to look at the 2 comma 3 element in the product, that is 4 times 3 plus 0 times 7 plus 2 times 1, which is equal to 14. Okay. Notice, even if matrices are square, so A times B and B times A can be defined, A times B and B times A can be defined. So in this case, this is a 2 by 2 matrix, this is a 2 by 2 matrix, so this multiplication is possible and the opposite multiplication is also possible. But the product is not necessarily the same. The first product is the 0 matrix. The second product is this very different matrix. So therefore, A times B is not necessarily equal to B times A in general. Also, AB equal to 0 does not necessarily mean A is 0 or B is 0, right? So over here, this is A, this is B, the product is a 0 matrix, but neither A nor B are 0 matrices. Later on, we'll see what specific properties that A and B must satisfy such that neither of them are 0, but the product is a 0 matrix. Okay. So this property basically says matrix multiplication is not commutative. That means A times B is not the same as B times A. But other properties for matrix multiplication are indeed satisfied. So K times A times B is the same as K times A times B, is the same as A times K times B. So scalars can move around. So this scalar, this number can instead move around. That's okay. And it's associative. So associativity is indeed true. What that means is I can first compute B times C and then multiply it with A, or I can compute AB and then multiply it with C. Now, this actually requires proof. It's not obvious at all, right? We saw that matrix multiplication is not commutative, so AB is not equal to BA. So clearly matrices aren't behaving like numbers. Also, it's possible for AB to equal the zero matrix, but A is not equal to zero, B is not equal to zero. So clearly matrices aren't behaving like numbers. But this particular property is indeed true. In this case, matrices do behave like numbers. It requires proof of associativity of matrices. And I'm going to ask you guys to do this as a Piazza bonus question. Piazza bonus question. I'll make a post about it on Piazza bonus question. So you'll be required to prove this on Piazza. Okay. Similarly, distributivity does hold. So this is true. This is true. Now, the basic punchline is that the order of the factors should be observed very carefully. As long as you do that, then matrices do indeed look a little bit like numbers. One compact way of thinking about matrix multiplication is, so suppose you have a matrix A, some matrix A, some matrix B like this, then the matrix multiplication corresponding to C is equal to A times B, C, or in here, sorry, C is equal to A times B can be viewed as taking the first row here and the first column here. So the 1, 1 element, the 1, 1 element of C is the dot product between the first row. It's the dot product between A1, which is a row vector, the first row vector, and B1, which is the first column vector. Right? Column vector of B is the first row vector of A. So in general, the CJK is the same as the matrix multiplication of the jth row vector of A and the kth column vector of B. And if you think about it, this type of matrix multiplication, where one row is multiplying one column, is actually nothing but a dot product. You must have already studied dot products of vectors. Dot product of this row vector with the other column vector. Okay, my tablet is behaving weirdly, but let's continue. So okay, all right. So moving on. All right. So let's finish this video here, and then we'll talk more in the next video about some properties of matrix multiplication.